Okay, we've made an example of pixel coordinates or polar coordinates, whichever way you want to look at it, where 0, 0 would be the top of the screen, top left-hand corner, for instance. Let me put a value of 2 in the x and 2 in the y, and we'll have a glance at that. And there's our pixel, way up there, 2 places over and 2 places down, right? So 0, 0 would be all the way up there in the top corner. So now I'd like to do an example of Cartesian coordinates. Now, what exactly are Cartesian coordinates? Well, allow me to transition over here to my visual references. Anybody that took basic trigonometry, I guess in high school or early college, would know that y is up, and x is to the right, and z goes off into the 3D distance, right? Now, let's see. Sorry. There. And likewise, if you go in the opposite, in negative, then you would be going below, underground, essentially, or so y is up in space terminology, and negative y is when you crash down into Earth pretty far, I guess. Z is the same, x and y, right? So, then, okay, yeah, so that was y is up in the positive, but then when we go to your polar coordinates, now y is down, technically. Imagine you're at the North Pole, and there's no up, all you can go is down, right? I guess that's the concept of polar coordinates. So we're shifting the polar coordinates from the center of the screen up to the top left-hand corner, also known as pixel coordinates, right? And so I remember when I was on Khan Academy, people would ask, people that were familiar with 3D programs, why in the world is y down? This makes no sense. And the reason for that is because your CRT monitors refresh the screen from the top left-hand corner down, as in the illustration, you see. Whereas before that, in the earlier days, you had something similar to an oscilloscope. And in fact, some of the early video games were arcade games, still used oscilloscope, and you can see here the little graph on the screen, and 0, 0 would be the center of the screen, and it would shine a photon, like a single television photon, onto the screen, and well, it wouldn't shine it onto the screen, would shine it onto a mirror, and then the mirror could be easily controlled with some electromagnets, so you could flip from place to place. If you wanted to do a pixel in one corner and then another pixel in the other corner of the screen, and jump from one quickly to the other, it might leave a trail, right? So what they do is you'd coat the screen with some phosphorus or something, so there was a slight delay from the time that the light beam hit the screen till it actually started to glow. Minimal amount of time, but just enough so when you flip over there real quick, it didn't leave lines between point A and point B, and you could draw in vector. This all used vectors, from starting at 0, 0. Okay, so and then of course, then there's an even smaller faction of people that would swear up and down that z is up. And why is that? Well, if we go all the way back to the early days when you had your very first video game, Pong, essentially, or early video games, it was tabletop. And I remember these would be in the bars and everything, and everyone played them. And the idea was it was like a soccer game. And so when you went from one side of the field to the other, you were going in Z, right? Okay, straightforward. And then later, they took Pong and they stood it up into your arcade games, along with other arcade games that were spawned as a result of that. And somewhere down the line, I guess some newbie came along that was programming games that didn't take basic trig, and didn't understand that Y was up, and just readily accepted now that Z was up, and so the legacy lives to this very day. Right? Okay, so enough talk about that. Let's get on with trying to convert our actual code quickly to our Cartesian coordinates. Jeez. Okay, so let's see. First thing I want to do, I'm going to add the screen width in down here too. We're going to use that. I'm sorry, we already have screen width. Let's go with screen height. There you go. DW 200 is our screen height. Okay, we'll use that for our calculation in a moment here. So let's see. I have AX here. I'm going to keep that. Only we're going to start right off with our screen height. Put the screen height in there. Okay. So what we want is half of the screen height, technically. So what I'm going to do is divide the screen height in two. And a quick way to do that would be just to shift right all of the bits. If you've been following along the binary part, if you shift to the left, you're multiplying by 2 in binary, and if you shift to the right one place, you are dividing by 2. Okay, pretty nifty. Okay, so then now we want to invert, so y is up instead of down, as in this example here. So we'll basically just subtract now from AX our y position, which is, let me just grab this, put that there, and say y here, just because. Okay. There we go. So that takes care of getting some things, okay, into that takes care of our y, basically. Okay, so now let's see. I've used up AX and BX here, so we're going to introduce yet another register here. We're going to move into CX now, our screen width, because we're going to, basically we're just going to take our position X and add a little offset to it, or yeah. So first we're going to get our screen X, screen width here, this value here. Okay, and then same thing as before. We're just going to go shift right to divide CX by 2. Very nifty. Okay, now that we got that out of the way, let's see. Here we are adding, before we just took the raw X value and put it in there. Now we're just going to add CX. Yeah, add CX instead of AX. There we go. Yeah. Okay, and then here, let's see, then instead of moving AX into DI, we'll move CX there. So hopefully that should be the correct chain of calculations. Let me save and see how badly I messed up. Well, okay. Okay. I'm sure you all saw that long before I did. Let's try this. See what we got. Okay, I got a pixel that's over here at 320/200. Why is that? Well, we haven't changed our screen coordinates for one. This should be 0, 0. Let's have a look. Okay, that is not correct either. Why is that? Oh, I'm sorry. I missed. I didn't change the correct values here. This should be 0, 0, and I don't think that is correct either. Why is that? Okay, I got my x is correct. Why is my y not correct? Let me just do a quick rundown here. Screen width, multiply bx, right? Cx, screen width, shift right, cx position x. One more thing here. Oh, I see what I add. Now that I have AX, I overwrote part of this where I add the AX. Add everything that I have calculated into AX, so we can go ahead and print that out. Is that correct? DI AX. See what happens here. There. Center of the screen. Let me see something here. Move DI. Yeah, I have to add the value into AX first, the value of our screen width. So CX is going into AX first. And then once it's all calculated, we can take AX and print it to the screen, and we have our final calculation now. Where 0, 0 is the center, and let's say I put, oops, not that one. In the Y, let's say I want to go up now. I go 50 up. There you go. Y is up. So that is your Cartesian coordinate system. What's nice about it now, I mentioned in the previous polar coordinate video, like now it's easy to go off screen, you know, but this is even easier because if I go off screen on the left, I don't have to deal with if it's less than 0. You know, I have this, I know my screen width and my screen height. And so now if I want to, yeah, for whatever reason, I have a character that goes off screen and it won't wig out, come in on the other side of the screen. I can do some calculations on it before it actually gets printed to the screen. There. So nifty. That is a convenient way to work. I may continue doing my more tutorials using the Cartesian coordinate system because of the convenience that I just mentioned. I could go either way, really. I'm usually used to working with the polar coordinate where y is down and everything, and I imagine most of the viewers are too, so I'm kind of torn, you know, but we'll see which way it goes. That is Cartesian coordinates.